The tactical evolution. How deflection mastery changed air combat. As American pilots and gunners became proficient in deflection shooting, it changed the entire nature of air combat. Tactics evolved to take advantage of improved gunnery, and these new tactics, in turn, drove further refinements in training. The relationship between skill and tactics created a positive feedback loop that made American air power increasingly effective. In the early stages of the war, American fighter tactics were relatively conservative. Pilots sought ideal firing positions directly behind the enemy aircraft, where deflection was minimal and the target was stable. This 6 o'clock position had been considered the optimal attacking position since the First World War. It allowed pilots to use their speed to close on an enemy, then follow behind, matching the target's maneuvers while firing from directly astern. However, achieving this ideal position was difficult. Enemy pilots knew it was dangerous and maneuvered aggressively to prevent anyone from getting on their tail. Engagements often became extended tail-chasing affairs, with one aircraft pursuing another through a series of turns and maneuvers trying to get that perfect rear position. Meanwhile, other enemy aircraft might enter the fight, and the pursuing pilot could himself become pursued. As American pilots became skilled in deflection shooting, new tactics became viable. Instead of spending valuable time and fuel maneuvering the human stories, aces and gunners. Behind the statistics and tactics were individual human beings, young men who learned deflection shooting and applied it in the most demanding circumstances imaginable. Their stories illustrate both the challenge of mastering this skill and its crucial importance in survival and success. Consider Major Richard Bong, America's highest-scoring ace with 40 confirmed victories. Bong wasn't a natural pilot when he entered training. Instructors noted that his flying skills were merely adequate. What set Bong apart was his gunnery. He obsessively practiced deflection shooting, spending extra time on the range and repeatedly reviewing his gun camera footage. Bong developed an almost supernatural ability to judge the correct lead for any angle of attack. In combat, Bong's tactics reflected his confidence in his deflection shooting. Rather than following enemy aircraft through extended maneuvers, he would position himself for a single high-deflection shot, take it, and achieve a kill. Fellow pilots marveled at his ability to hit targets at angles where they themselves wouldn't even attempt a shot. When interviewed about his success, Bong credited his shooting ability above all else, noting that many pilots could fly well enough to get into position, but few could consistently hit what they aimed at. Captain David McCampbell, the Navy's leading ace with 34 victories, demonstrated the importance of ammunition discipline combined with deflection shooting. During one legendary engagement, McCampbell and his wingman encountered a formation of 60 Japanese aircraft. Rather than spraying fire wildly, McCampbell carefully took deflection shots, firing only when he had a clear lead on a target. He shot down 9 aircraft in this single engagement, becoming an ace in a day, and had ammunition remaining when the fight ended. His success came not from superior aircraft or numerical advantage, but from superior shooting skill. On the bomber side, consider Staff Sergeant Michael Aruth, a B-17 ball turret gunner with the 8th Air Force. The ball turret, a spherical gun position hanging beneath the bomber, was cramped, uncomfortable, and terrifying. Aruth sat curled in this tiny space for hours during missions, watching the ground thousands of feet below through the turret's glass panels. When enemy fighters attacked from below, Aruth had to track them, calculate deflection while hanging upside down, and engage them while his entire bomber shook from engine vibration and evasive maneuvers. Aruth was credited with 5 confirmed kills and several more probables. Exceptional performance for a gunner position that was inherently difficult to shoot from accurately. When asked his secret, Aruth explained his methodical approach to deflection shooting. He'd memorized the silhouettes and sizes of different enemy aircraft types.
When one appeared, he'd instantly identify it, estimate range based on its apparent size, and calculate the required lead. Then he'd place his tracers ahead of the target, watching for strikes. His disciplined approach and thorough understanding of deflection principles made him one of the most effective
Legacy: deflection shooting in modern warfare. The lessons learned from World War II deflection shooting have echoed through the decades, influencing how military forces train for air combat, even in the jet age and beyond. While technology has advanced dramatically, the fundamental challenge, hitting a moving target from a moving platform, remains essentially unchanged. In the Korean War, just a few years after World War II ended, American pilots faced an unexpected challenge: the MiG-15, a Soviet-designed jet fighter that outperformed American jets in some key areas. Yet American pilots achieved a favorable kill ratio, shooting down approximately 10 MiGs for every American aircraft lost in air-to-air combat. While this success had multiple causes, superior training in deflection shooting was consistently cited as a key factor. American pilots, many of whom were World War II veterans or trained by World War II veterans, had internalized deflection shooting principles. They understood how to lead a target, how to adjust for relative motion, and how to make effective high-deflection shots. Many Soviet and Chinese pilots, despite having capable aircraft, hadn't received the same depth of gunnery training. They would aim directly at targets and miss, exactly as American pilots had done in early World War II before the training revolution. The Vietnam War presented new challenges. The emphasis on missile armament in early jet fighter designs meant some aircraft, like early versions of the F-4 Phantom, didn't even carry guns. The theory was that long-range missiles had made dogfighting obsolete. This theory proved disastrously wrong when missiles were unreliable and many engagements occurred at ranges where only guns were effective. American pilots found themselves in gun combat without adequate training in deflection shooting. The institutional knowledge had partially eroded during the missile focus era. Kill ratios dropped alarmingly. In response, the Navy established Top Gun, formerly the Navy Fighter Weapons School, specifically to address this training deficiency. Among the key skills taught was deflection shooting.
The experimental journey, methodical innovation. Hale's approach was systematic. He began by thoroughly reviewing existing literature on high explosives. TNT was well understood, but it wasn't the fastest detonating explosive available. RDX, cyclotrimethylene trinitramine, also known by the British designation Research Department Explosive, exhibited detonation velocities approaching 8,750 meters per second, nearly 27% faster than TNT. RDX had been synthesized as early as 1899 by Georg Friedrich Henning in Germany, but it remained a laboratory curiosity for decades. It was more expensive to produce than TNT, more sensitive to accidental detonation, and difficult to manufacture in large quantities. The British had developed production methods during the 1930s, recognizing its potential for specialized applications, but it remained an exotic material. Hale's initial experiments with pure RDX in shaped charges were promising. Penetration tests against steel plate showed measurable improvement, perhaps 20 to 30% better than equivalent TNT charges. But the results were inconsistent. Some test shots would achieve impressive penetration, others would barely outperform the TNT baseline. High-speed photography revealed the problem. RDX's high detonation velocity was creating too rapid a collapse of the cone liner. The resulting jet was traveling faster, but breaking up almost immediately after formation. This was the paradox that had stumped other researchers. More energetic explosives should logically produce better penetration, yet beyond a certain threshold, performance actually degraded. Hale recognized this as a material coherence problem, The jet needed to maintain its form long enough to interact with the target, typically traveling 2 to 3 cone diameters of standoff distance before impact. At velocities exceeding certain thresholds, the jet would fragment from internal stresses before reaching the target. The solution Hale intuited wasn't pure RDX. It was a blend, a mixture that would balance detonation velocity with other crucial properties. He began experimenting with various combinations, treating explosive formulation like a master chef developing a recipe. Each ingredient contributed specific characteristics. The art lay in achieving perfect balance. His laboratory notebooks from this period, now partially declassified, revealed the meticulous nature of his work. Entry after entry documents subtle variations. Composition 14, RDX 85%, TNT 15%, detonation velocity measured at 8,100 meters per second, penetration 4.2 inches at optimal standoff, jet coherence poor beyond 2.5 diameters. Composition 21, RDX 78%, TNT 15%, wax binder 7%, detonation velocity 7,950 meters per second, penetration 4.8 inches, improved coherence but velocity insufficient. Composition 29, RDX 88%, TNT 10%, aluminum powder 2%, detonation velocity 8,300 meters per second, penetration 5.1 inches, jet stability excellent, but premature breakup at 3+ diameters. The aluminum powder addition was particularly interesting. Aluminum doesn't contribute significantly to detonation velocity. It actually reduces it slightly. However, fine aluminum particles within the explosive matrix serve as hotspots that help propagate and stabilize the detonation wave. This creates a more uniform collapse of the shaped charge cone, improving jet quality at the expense of raw velocity.
The breakthrough. Composition B. After months of experimentation, Hale arrived at a formulation that balanced all the competing factors beautifully. He designated it Composition B, a deceptively simple name for a carefully engineered mixture. The formula consisted of 60% RDX, 39% TNT, and 1% wax as a desensitizing binder. The magic of Composition B lay in its synergy. The RDX provided high detonation velocity. The mixture achieved approximately 7,800 meters per second, substantially faster than pure TNT, but slightly slower than pure RDX. The TNT served multiple functions. It acted as a carrier matrix, making the mixture easier to cast and handle. It provided some desensitization, reducing the risk of accidental detonation, and critically, it modulated the detonation characteristics to produce more stable jet formation. The small quantity of wax, just 1%, played an outsized role. It further desensitized the mixture and improved its physical properties, making it less brittle and more resistant to cracking during storage and handling. In battlefield conditions, where rockets might be subjected to extreme temperatures, rough handling, and long periods in storage, these physical properties were as important as explosive performance. Initial penetration tests with Composition B were stunning. Against homogeneous steel armor plate, the new warhead penetrated 5.8 inches, more than double the performance of the original TNT charge. The improvement wasn't linear. It represented a quantum leap in capability. A tank that was essentially immune to the old warhead was now vulnerable through most of its armor profile. Hale didn't stop with initial success. He conducted extensive testing to validate the performance across variables, temperature extremes from -40 degrees Fahrenheit to +140 degrees Fahrenheit,
Varying standoff distances, different angles of impact, different armor types, including face-hardened and rolled homogeneous steel. The Composition B warhead performed consistently, meeting or exceeding penetration requirements across the full envelope of battlefield conditions.
The physics of penetration. Understanding the improvement. To understand why Composition B worked so effectively, we must delve deeper into shaped charge physics. When the explosive detonates, a detonation wave propagates through the charge at the material's characteristic velocity. This wave encounters the cone liner. In the bazooka's case, a copper cone with specific wall thickness and apex angle, typically around 42 degrees. The immense pressure of the detonation wave, on the order of 300,000 atmospheres, causes the copper to behave plastically. The liner collapses inward, with the material nearest the apex colliding with itself along the cone's axis. This collision creates conditions similar to two high-velocity streams colliding. The material squirts away from the collision point in both directions. The material that squirts forward becomes the penetrating jet. The material that squirts rearward forms the slug, which contributes little to penetration. The ratio of jet mass to slug mass is determined by cone geometry and collapse dynamics. For optimal performance, approximately 15 to 25% of the liner mass should become jet, with the remainder forming the slug. The jet doesn't penetrate like a drill or a bullet. Instead, it creates conditions at the tip where both the jet material and target material behave as fluids, despite being solid metals. The jet tip, traveling at 8,000 to 10,000 meters per second, creates pressures at the impact point exceeding the strength of any structural material. Both metals yield and flow around each other, with the jet creating a cylindrical cavity as it penetrates. The depth of penetration is governed by a surprisingly simple relationship discovered by researchers in the 1940s. The penetration depth is approximately proportional to the square root of the jet velocity multiplied by the jet length divided by factors accounting for material densities and strengths. Critically, jet velocity and jet length both depend heavily on the explosive's detonation velocity and pressure. Composition B's detonation velocity of 7,800 meters per second created jet tip velocities approaching 9,500 meters per second, a 15% improvement over TNT-based charges. More importantly, the jet maintained coherence over greater standoff distances. A coherent jet effectively has greater length in the penetration equation, leading to disproportionate improvements in penetration depth. The mathematics predicted approximately 75% improvement in penetration for the observed velocity increase and improved coherence. Field testing confirmed this prediction with remarkable accuracy. The Composition B warhead penetrated 5.8 inches compared to 3.3 inches for TNT, a 76% improvement.
Manufacturing challenges, from a laboratory to battlefield. Proving the concept in a laboratory is one thing. Manufacturing millions of warheads for field deployment is quite another. Hale's success created an enormous logistical challenge. The United States needed to produce RDX in unprecedented quantities, develop casting facilities for Composition B, integrate the new explosive into existing warhead designs, and retrofit or replace millions of existing munitions. RDX production presented the first hurdle. The existing British manufacturing process, developed at the Royal Arsenal at Woolwich, was adequate for small-scale production, but couldn't meet American wartime demands. The process involved nitrating hexamethylene tetraamine with concentrated nitric acid, a hazardous procedure prone to runaway reactions if not carefully controlled. American chemical engineers, working with Hale's input, developed a continuous flow process that dramatically increased production capacity while improving safety. Plants were constructed in Alabama, Tennessee, and Louisiana, far from coastal areas that might be vulnerable to enemy action. By mid-1943, these facilities were producing RDX at rates that would have been inconceivable just 2 years earlier. Casting Composition B required specialized facilities. The mixture had to be heated above TNT's melting point, approximately 80 degrees centigrade or 176 degrees Fahrenheit, to create a pourable liquid, then precisely combined with RDX powder and wax in heated mixing vessels. The mixture was then poured into warhead shells and allowed to cool under controlled conditions. Any impurities, air bubbles, or non-uniformities could compromise performance or create dangerous sensitivities. Quality control was paramount. Every batch underwent rigorous testing, chemical analysis to verify composition, sensitivity testing to ensure safety margins, and crucially, live fire penetration testing of sample warheads. Batches that failed any test were recycled, a laborious process of melting, separating components, and starting over. The retrofitting program presented its own challenges. Existing M6 warhead bodies could be reused, but the interior casting had to be completely removed and replaced. Millions of existing rockets required processing through depot-level facilities. Simultaneously, new production lines were manufacturing warheads with Composition B from the start.
Security and secrecy, the banned designation. The remarkable performance of Composition B didn't escape enemy attention. After initial combat use in late 1943, recovered American munitions became priority intelligence targets for German and Japanese forces. Both Axis powers conducted detailed analyses of captured weapons, attempting to reverse engineer the explosive formulation. American security officials recognized the danger. If enemy forces duplicated Composition B, they could apply it to their own shaped charge weapons, potentially neutralizing Allied armor advantages. More concerning, they might develop even more advanced formulations, creating a technical arms race in explosive chemistry. The solution was comprehensive information control. Composition B's exact formulation was classified at the highest levels. Manufacturing personnel had security clearances and worked under strict compartmentalization. Workers at one stage of production didn't know details of other stages. Even the RDX production facilities were described vaguely in official documents as high explosive manufacturing. The term banned emerged from this security regime, though it was somewhat misleading. Composition B wasn't banned in the sense of being prohibited. Rather, information about it was restricted through classification. Documents referencing the specific formulation carried special handling designations. Discussion of the explosive's composition outside secure facilities was forbidden. Personnel who worked with the material signed binding non-disclosure agreements. This security extended to technical publications. Pre-war explosive chemistry textbooks and journals had freely discussed various RDX formulations. During the war years, scientific journals voluntarily suppressed such information. Researchers working on energetic materials submitted their findings to military review boards before publication. Many discoveries remained classified for decades. The security regime worked largely. German intelligence obtained some information through captured materiel and interrogated prisoners, but never achieved full understanding of American manufacturing processes. Japanese intelligence faced even greater challenges. Isolated from European scientific exchanges and lacking advanced chemical industry infrastructure, Japanese efforts to duplicate American explosives lagged significantly. This technical gap contributed to the relative ineffectiveness of Japanese anti-tank weapons throughout the Pacific Campaign.
Combat performance, the proof in battle. The ultimate test of any weapon is battlefield performance. Composition B warheads entered combat in multiple theaters during late 1943 and early 1944, and the results quickly became apparent to frontline troops. In Italy, American infantry faced improved German defensive positions, including dug-in Panthers and Tigers. Previous encounters with these formidable tanks had been costly and demoralizing. American Sherman tanks were outmatched, and infantry anti-tank weapons seemed ineffective. The new bazooka rockets changed the tactical equation. Infantry teams could now engage German armor with reasonable confidence in their weapons' effectiveness. Reports from company and battalion commanders noted marked changes in infantry morale and tactical approaches. Units that had previously avoided confrontation with German armor now actively hunted enemy tanks, using terrain and concealment to close to effective bazooka range, typically 100 to 300 yards. The psychological impact on German tank crews was equally significant. Armor that they had considered near impervious to infantry weapons was suddenly vulnerable. In one documented engagement near Cassino in January 1944, a single American infantry company claimed 3 Panzer IV and 1 Panther destroyed or disabled with bazooka fire over a 2-day period. The engagement reports, later analyzed by Army Ground Forces observers, noted that all penetrating hits were achieved against side or rear armor. The improved penetration allowed infantry to exploit tactical positions that would have been marginally effective with the older warheads. The Pacific Theater presented different challenges. Japanese armor was generally lighter than German, making it vulnerable to the original TNT warheads. However, Japanese defensive tactics increasingly relied on concrete bunkers and fortified positions. The Composition B warheads, while designed for armor penetration, proved devastatingly effective against concrete and reinforced earth positions. The high-velocity jets could punch through 2 feet of reinforced concrete, performance that made them valuable against Japanese pillboxes and bunkers throughout the island-hopping campaigns. Statistical analysis of after-action reports revealed compelling data. American forces reported approximately 73% higher engagement success rates with bazooka rockets after Composition B warheads became standard issue. Engagement success was defined as achieving a mission kill, permanently disabling the target through mobility kill, firepower kill, or catastrophic kill. The improvement correlated directly with warhead penetration performance.
Technical evolution, building on success. Composition B represented a landmark achievement, but explosive chemistry didn't stop evolving. The principles Hale established, balancing detonation velocity with jet coherence, optimizing binder materials, ensuring manufacturability, guided subsequent development efforts throughout the war and beyond. Researchers explored enhanced variations. Composition B3, developed in 1944, substituted aluminum powder for some of the TNT, achieving slightly higher penetration performance while maintaining stability. The aluminum contributed to afterburn effects, sustained high temperatures in the penetration channel that could ignite fuel or ammunition in armored vehicles. British researchers developed their own RDX-based mixtures with different optimization priorities. Torpex, combining RDX with TNT and aluminum, maximized total energy output for underwater explosive effects. Though less suitable for shaped charges due to different detonation characteristics, it demonstrated the versatility of RDX-based formulations for specialized applications. The shaped charge principle itself underwent refinement. Engineers experimented with cone liner materials beyond copper. Tantalum, with its extraordinary density, produced higher velocity jets. Glass liners created unique penetration mechanics. Bimetallic liners, combining different metals in the cone, offered variable penetration characteristics. Standoff distance optimization represented another frontier. Engineers recognized that penetration peaked at specific standoff distances, typically 2 to 3 cone diameters from the target. Too close, and the jet hadn't fully formed. Too far, and the jet had begun to break up. This led to extended nose probes on anti-tank warheads, ensuring optimal detonation distance regardless of impact angle or target surface irregularities. Post-war development accelerated. The emergence of reactive armor,
explosive tiles mounted on tank hulls that disrupted incoming shaped charge jets, spurred development of tandem warheads. The first charge would trigger the reactive armor. A second charge, following milliseconds behind, would penetrate the now exposed base armor. Such sophisticated approaches built directly on the understanding Hale and his contemporaries had established.
The human element, stories from the field. Behind every technical specification and penetration measurement were soldiers whose lives depended on their weapons' effectiveness. The improvement from Composition B warheads often meant the difference between survival and catastrophe for infantry facing armored opponents. Sergeant James Mackenzie, a bazooka gunner with the 1st Infantry Division, later recounted an engagement near St. Louis in June 1944. His squad had established a hasty ambush position along a hedgerow as German armor probed American lines. A Panther tank appeared, its 75mm gun traversing menacingly. Mackenzie's assistant loaded one of the new rockets, visibly different from the older models, with updated markings and slightly different balance. "I'd hit Panthers before with the old rockets," Mackenzie recalled in a 1980 interview. "You'd see the flash, hear the bang, and then watch your rocket bounce off like you'd thrown a rock. This time was different. The flash looked bigger, hotter somehow. The tank stopped dead. Smoke started pouring from the engine deck. The crew bailed out fast. That's when I became a believer in the new ammo." Similar stories emerged from across the European theater. In the Ardennes, during the desperate days of the Battle of the Bulge, American infantry armed with bazookas formed the backbone of the defensive effort against German armored spearheads. The improved warheads allowed small infantry teams to hold critical road junctions and villages against German tank columns that would have broken through months earlier. The psychological dimension shouldn't be underestimated. Soldiers who trust their weapons fight more effectively. The visible improvement in bazooka performance, seeing enemy tanks disabled where previously they'd seemed invulnerable, boosted infantry confidence and willingness to engage. This intangible factor contributed to tactical success in ways difficult to quantify, but readily apparent to commanders at all levels. Scientific legacy. Hale's lasting impact. George Hale's work on Composition B extended far beyond its immediate military application. The systematic approach he pioneered, balancing multiple performance parameters, rigorously testing across operational envelopes, optimizing for both performance and manufacturability, became standard methodology in energetic materials research. Post-war, Hale continued his research at various institutions. He consulted for military research laboratories, contributed to civilian explosive development for mining and construction, and trained a new generation of explosive chemists. His 1952 textbook, Practical Explosive Chemistry, became the standard reference for 2 decades, training engineers and chemists worldwide. The principles underlying Composition B found applications far beyond shaped charges. Modern mining explosives, demolition charges, and even some commercial applications trace their lineage to the balanced formulation approach Hale exemplified. The understanding that optimal performance comes from careful mixture design rather than simply using the most powerful available explosive influenced everything from tunnel boring to controlled demolition. Military shaped charge technology continued evolving through the Cold War and beyond. Modern anti-tank missiles like the Javelin or Tau achieve extraordinary penetration, often exceeding 30 inches of rolled homogeneous steel equivalent. They employ explosives that are descendants of Composition B, with incrementally improved characteristics achieved through 70 decades of additional research. Yet the fundamental principles remain those Hale established: balance detonation velocity with jet coherence, optimize liner collapse dynamics, and ensure reliability across operational conditions. Manufacturing innovation, industrial-scale production. The successful deployment of Composition B warheads required an industrial achievement comparable to the scientific breakthrough itself.
At peak production in 1944, American manufacturers were producing over 500,000 bazooka rockets monthly, each containing precisely formulated and cast Composition B explosive. This industrial scale demanded innovations in chemical engineering and manufacturing process control. The continuous flow RDX production process, while safer than batch methods, required sophisticated monitoring and control systems. Temperature, pressure, and reactant flow rates had to be maintained within tight tolerances to ensure consistent product quality and prevent hazardous excursions. The casting facilities represented another engineering challenge. Molten Composition B had to be maintained at optimal temperature, hot enough to flow freely, but not so hot as to risk thermal decomposition. Filling equipment required precision engineering to avoid air entrapment while ensuring complete filling of complex warhead geometries. Cooling had to be controlled to prevent thermal stress cracking. Quality assurance systems developed for Composition B production set standards that influenced post-war explosive manufacturing. Statistical process control, then a relatively novel concept outside a few advanced industries, became standard practice. Every batch underwent chemical analysis. Samples from every day's production underwent live-fire testing. Traceability systems ensured that any field-reported defect could be traced back through the manufacturing chain to identify root causes. The workforce required for this industrial expansion was itself a logistical challenge. Tens of thousands of workers, many of them women entering industrial employment for the first time, received training in handling energetic materials safely. The safety record, while not perfect, was remarkably good given the scale and pace of production. This reflected careful attention to process safety, worker training, and facility design.
International dimensions, Allied cooperation, and competition. The development and deployment of Composition B occurred within a broader context of Allied technical cooperation and competition. American, British, and Canadian researchers shared information about explosive formulations, shaped charge design, and manufacturing techniques, but not without friction and occasional rivalry. British researchers had pioneered much of the early RDX work, and some British scientists felt that American developments represented insufficient acknowledgement of British contributions. The reality, as always, was nuanced. British theoretical work and initial RDX production methods provided crucial foundations. American engineering scaled these concepts to industrial production levels that British industry, strained by years of war and resource constraints, couldn't match. Canadian contributions, often overlooked, were significant. Canadian chemical plants produced substantial quantities of RDX using processes that represented independent innovations on British methods. Canadian researchers at the Valcartier facility contributed to shaped charge optimization and conducted extensive cold weather testing that informed warhead design for winter operations. Soviet development of shaped charge weapons followed an independent but parallel path. Soviet researchers achieved similar performance improvements using their own explosive formulations. Post-war analysis revealed that Soviet shaped charge technology by 1945 roughly matched American capabilities, achieved through independent research with minimal information exchange. This parallel development underscored that the theoretical foundations were sufficiently well understood internationally that multiple research efforts could reach similar conclusions. German-shaped charge development, ironically, had begun the war ahead of Allied efforts. German Panzerfaust and Panzerschreck weapons were effective anti-tank systems that influenced Allied designs.
However, German research became increasingly disjointed as the war progressed. Allied bombing disrupted production facilities and research centers. Material shortages forced compromises in explosive formulations. By 1944, German shaped-charge technology, while still formidable, had been overtaken by Allied advances.
The cost of innovation, resources, and priorities. Developing and deploying Composition B required enormous resource allocation during a period when every material, every factory, and every researcher was desperately needed for multiple critical projects. The decision to prioritize this development represented hard choices by military planners and political leaders. RDX production consumed nitric acid that might otherwise have been used for other explosive production. Manufacturing facilities required construction materials, steel and concrete, in perpetual shortage. Skilled chemical engineers and technicians working on Composition B weren't available for other projects. Every resource committed to improving bazooka warheads was a resource unavailable elsewhere. These decisions were made in the context of competing priorities. The Manhattan Project consumed vast resources developing atomic weapons. Aircraft production and radar development demanded materials and expertise. Naval construction competed for steel and manufacturing capacity. In this environment of resource scarcity and competing demands, allocating resources to improve infantry anti-tank weapons required convincing justification. The case for Composition B rested on its practical impact. Infantry anti-tank capability had direct, measurable effects on battlefield outcomes. Every German tank disabled or destroyed by improved bazooka fire was one less threat to Allied infantry and armor. The psychological boost to infantry morale had tangible effects on tactical performance. The relatively modest resource requirements compared to major weapon systems like tanks or aircraft made the cost-benefit analysis favorable. Post-war analysis vindicated these decisions. Studies of weapons effectiveness concluded that improvements to infantry anti-tank weapons, including the Composition B warhead, contributed significantly to Allied tactical success at lower cost per battlefield effect than many more resource-intensive programs. This doesn't diminish the importance of other developments, radar, proximity fuses, improved armor, better aircraft, but demonstrates that even incremental improvements to existing systems could yield substantial returns.
Conclusion: the enduring significance. George Hale's development of Composition B represents more than a technical achievement, though the technical accomplishment was substantial. It exemplifies how systematic scientific inquiry, careful engineering, and industrial scale-up can combine to solve critical practical problems. The methodology Hale employed, understanding the physics governing device performance, systematically varying formulation parameters, rigorously testing against operational requirements, and ensuring manufacturability, remains the standard approach for complex technical development. The immediate impact was clear. American infantry gained a reliable, effective anti-tank weapon that helped level the battlefield against superior German armor. The penetration improvement from roughly 3 inches to nearly 6 inches represented a qualitative shift in capability. Tanks that had been nearly immune to infantry weapons became vulnerable. Tactics evolved accordingly, with infantry taking more active roles in anti-armor operations. The longer-term legacy extends beyond World War II applications. Modern shaped-charge weapons, from shoulder-fired anti-tank missiles to vehicle-mounted systems, employed direct descendants of Composition B. The explosive formulations have evolved. Modern compounds offer incrementally better performance, improved safety margins, and insensitivity to accidental initiation. But the fundamental approach of balancing multiple performance characteristics traces directly to Hale's work. The banned designation, while somewhat mythologized in popular accounts, reflects the genuine security concerns surrounding technological advantages in wartime. Protecting technical innovations from enemy duplication remains a constant challenge in military technology.
The comprehensive information security surrounding Composition B set patterns for technology protection that continue today in more sophisticated forms. For the thousands of soldiers who carried bazookas into combat, the technical details mattered less than the practical result. Their weapons worked. They could engage enemy armor with confidence rather than desperation. This battlefield effectiveness, achieved through the work of scientists and engineers thousands of miles from the front lines, exemplifies how technological innovation directly supports those who face combat's harsh realities. The story of Composition B reminds us that major technological advances often emerge not from single eureka moments, but from methodical work by dedicated researchers solving clearly defined problems. Hale didn't discover a miraculous new explosive. RDX had been known for decades. His achievement was identifying the optimal combination of known materials to meet specific performance requirements, then ensuring that optimal combination could be manufactured at the scale and pace demanded by global war. As we face contemporary challenges, whether military, industrial, or scientific, the lessons remain relevant. Systematic inquiry, rigorous testing, balanced optimization across multiple parameters, and attention to practical implementation constraints continue to define successful technical innovation. The chemist's banned powder mix that made bazooka rockets penetrate 6 inches of German steel stands as a lasting example of how science, properly applied, can change the course of history.